Hello. Today I want to talk about computing triple integrals in cylindrical and spherical coordinates. And I want to make sort of a hybrid of two different web work problems that we've had. One in the past and one that's due next. All right, so let's start with this region. Let W be a region in R3. That means W is a subset of R3. Or possibly equal to, but it's not all of R3. Let W be a region in three-dimensional space above the cone with an angle of 90 degrees with its vertex at the origin and below the sphere of radius 7. As in one version, at least my version of set 15.3, problem 5. You might remember that you had to set up the integral to in Cartesian coordinates to integrate over that region. And I said at the time, it's really stupid to integrate this using Cartesian coordinates. Okay, so write an iterated integral for the volume of that region. The volume of W is just a triple integral over W of dV. Or you could say 1 dV, but the one is optional. So set that integral up in Cartesian coordinates, in spherical coordinates, and in cylindrical coordinates. All right, so the main thing to do is first thing to do is to figure out what this region looks like, and I'm going to share the screen. All right, so here is that region from the previous set. Oh, actually, no, this is the homework problem that's due next. It's a little bit like W, but it has a flat top. So you're going to be setting up, defining the volume of this region with the flat top. But let's go back to this region that you might remember that has the sphere at the top and the cone at the bottom. Now, I have also set up a picture of that. Here is an intersection of the regions. In fact, I'm starting to use spherical coordinates. We have rho equals 7 is the equation of the sphere of radius 7. And get rid of that. And then phi equals pi over 4 is the equation for that cone, right? The full angle of the cone was 90 degrees, or pi. Full angle of the cone is 90 degrees, or pi over 2. So that's the angle of the size of the cone from the vertical is half that pi over 4. So phi equals pi over 4 is the equation of that cone. All right. I also mentioned that we'll be getting to this later. There's another way to look at that. Let me see, get rid of that. Here is a picture of that surface. Later, we'll be talking about how to parameterize that surface using parameterization. And so here, U is sort of like the R and theta. Let me just click on it so we see that. So U goes from, or R goes from 0 to 7 over square root of 2. V or theta goes from 0 to 2 pi. And that traces out, this guy here traces out the top of the cone, the top of the sphere, and then this part here traces out that part of the cone. All right, so that's sort of what the region looks like. A little bit hard to see if we just look at these two. It might help to look at the transparency. You see, it's inside the sphere is the region and above that cone. All right. Stop sharing. All right, so let's remind ourselves that what we've got to do is write that region in various ways. Actually, it's a little script W. All right. So it's, let's start with, well, let's start here with polar with spherical coordinates, because that's really the best. So let's do rho theta phi. That's in spherical coordinates. Those are all points in R3 with spherical coordinates, such that what do we have here? Well, we have 0 less than or equal to rho less than or equal to 7. So this means inside the sphere of radius 7. And we also need that 0 less than or equal to phi less than or equal to pi over 4. Again, there's the region here. The region looks like this. At least mine has a 90 degree, which is pi over 2 angle here at the cone. What that means is that this angle is pi over 4. So phi goes from everywhere from straight up, phi equals 0, to pi over 4. And finally, 0 less than or equal to theta less than or equal to 2 pi. I go all the way around the circle. On the board. Good. All right. So, as usual, as I said, as usual, this is just going to be an integral between fixed limits. So none of these limits of integration have dependence on the other variables. So it's just a really nice one to integrate. So here the volume of W, triple integral over W of dV is going to be, using this, I'm going to integrate from 0 to 7 with respect to rho. I'm going to integrate from 0 to pi over 4 with respect to pi. And I'm going to integrate from 0 to 2 pi with respect to theta. But I have to put something in here. There's a 1 for the integrand, but I need the rho squared sine phi, because that is, this whole thing is the volume element, dV. So this whole thing is really 1 times dV or just dV, it doesn't matter, right? All right, well, like I say, this is the kind of thing we like. We're integrating over 3 variables, and the thing we're integrating is just a product of a function of rho times a function of phi times a trivial function of theta. So I guess we can do it in that order here. We go from 0 to 7, that's the rho integral, and I do rho squared d rho multiplied by to pi over 4 of sine phi d phi. Okay. Times the integral from 0 to 2 pi of d theta. Well, let's do them in the easiest to hardest. This is just 2 pi. Theta evaluated 2 pi minus theta evaluated 0. This is equal to rho cubed over 3 from 0 to 7. And then this thing here is, let me see, derivative of sine is cosine, derivative of cosine is negative sine. I did negative cosine of phi between 0 and pi over 4. All right, let's think before I evaluate this. Let's draw a little triangle. Pi over 4. All right. And cosine is square root 2 over 2. All right. So this is going to be from this integral here. And then this is going to be negative square root of 2 over 2 minus -1. 2 pi. All right, so there's going to be 1 minus 2 over square root of 2. Maybe I should, I don't know, let's take, multiply that 2 by here and that by here. So this is going to be 7 cubed over 3. Okay, and then I can multiply everything through by 2. That's going to be, it was plus 1, now it's 2 minus square root of 2. And then this pi. Okay. All right. So let's do the, by the way, let me just check if I did that right. No, I'm sure I did that right. I'm going to check them off the end. Although somebody is knocking at the door, there's a classroom start. Class starts in here at 3 o'clock, but it's only 2:30, 2:24. So anyway, they can wait a bit, but I should not be too long. Let's do the next one. What's the other, what is the way to the coordinate system? The way to do this with cylindrical coordinates. So in cylindrical coordinates, probably a good idea to draw a little picture. R and Z, the picture looks like this, right? Because this here, if I take this thing and spin it around, I get that cone, right? So what I'm doing is I'm drawing a picture of this part of the cone that I spin around. So theta goes from 0 to 2 pi. Here's the R radius, the distance from any point to the z-axis. And this is R squared plus Z squared with 7 squared on top. And this is R equals Z on the bottom. Okay, if I solve that one for Z, I get Z squared is 7 squared minus R squared, or Z is square root of 49 minus R squared. That's the top. And Z equals R is the bottom. Right, there's Z. That Z is that square root of 49 minus R squared. There's Z equals R. All right, so another way of writing W is that it's all R theta Z. Those are cylindrical coordinates. All those points in R3, those cylindrical coordinates are such that, well, let's see. Oh, I've got to figure out what this point is here. What is this point, that here? When those intersect, we have, what do we have here? They have the same Z. So we have R equals square root of 49 minus R squared. That's the R value where the two Z functions meet, or R squared is 49 minus R squared. 2R squared is 49. R squared is 49 over 2. R is plus or minus 7 over square root of 2. And we're going to choose the plus. Okay? All right, so this number here is 7 over square root of 2. So now let's write this in the ready to integrate form. So sorry, you can pause the video and go back and look at it. Let's do it. So let's start with R. So 0 is less than or equal to R is less than or equal to that 7 over square root of 2 number. R comes out to here. 0 is less than theta is less than 2 pi. So I go all the way around the circle. And now Z is the complicated one. Z goes from R to this top here, 49 minus r squared. So now now I'm ready to write this as an iterated integral, but I have to make sure I put the z inside the r integral. All right, so the volume of W is going to be a triple integral over W of W of dV. And remember that dV is now going to be r dr d theta dz in some order. In fact, I'm going to have to put the z inside as we see. So this is going to be, let's take care of the easy one. Let's just do it in this order. R goes from 0 to 7 over square root of 2. That's what R does. And then what does theta do? It goes from 0 to 2 pi. That's what theta does. And now Z goes from R to square root of 49 minus R squared. That's what Z does, but I have to plug back in to turn this into the volume element. I've got to make sure I put in the R. That's basically it. I think in the interest of time, I'm not going to do the really gross Cartesian coordinate version. You can go back to the previous set. I do want to show you share the screen again and show you these computations with Mathematica. So share the screen, I got Mathematica going. I've got all of these integrals showing. Let's see, we have the first one that I did, I went from 0 to 7, 0 to pi over 2, 0 to 2 pi. And then I think I actually even wrote that. I got a number for that. And then here's the integral I just did, r dz d theta dr. And then r goes from 0 to 7 over square root of 2. Theta goes from 0 to 2 pi. Z goes from r to 49 minus r squared. Okay. And then this is, if you set it up with Cartesian coordinates, you get this gross expression. And what I've done here is I evaluated all these integrals in Mathematica. And then I have the timing. So this method took 0.36 seconds to do that integral. If I, when I broke it up, I did the theta integral by hand, and I had the other two integrals had it do it, and that it happened in about 1/10 of the time. Took a little bit shorter to do this Cartesian coordinate integral, but when I did the setup in Cartesian coordinates, I said this is the cylindrical. In Cartesian coordinates, when I did the integral in Cartesian coordinates, it took longer than 2 minutes, 127 or 128 seconds. I got the same answer, although plus 0 I, right? 0 real imaginary part. So it had a really hard time evaluating that. Like I said, it took more than 2 minutes, where this took significantly less than a second, a quarter second. 0.015, 15 thousandths of a second to do that, etc. All right.